Welcome to the course on advanced machining processes. Now we are going to discuss one hybrid process that is called rotational magnetorheological abrasive finishing process, or in brief we can say this one as RMRFF process. So this is the outline of my presentation. So what are the current status of recent these finishing processes, and then RMFF, rotational magnetorheological abrasive finishing experimental status and finishing mechanism we shall discuss. Then we shall discuss about the advantages of RMFF process with possible application areas, and then rheological characterization of polishing media. Then we shall discuss about the finishing experiments using flat workpieces, RMRFF finishing experiment with flat workpieces. Then we shall discuss RMRFF finishing experiment with cylindrical workpieces, internal surface of cylindrical workpieces. Then we shall discuss some CFD simulation, computational fluid dynamic simulation of polishing medium and surface modeling. Then we shall conclude. Now this current status of the related finishing technologies, you can see here this is the spiral polishing which is developed by Yan et al. At 2007. Okay, so here you can see one spiral tool is there. Okay, so this spiral tool, so this is the bottom chamber, this is the top chamber. Okay, so this initially this bottom chamber it is filled up with the polishing medium, viscoelastic polishing medium. As the spiral tool is there, as the spiral tool rotates, okay, so this polishing medium it will through the groove of the spiral tool it will try to come to the top media cylinder. Okay, so while coming to the top media cylinder, if you keep workpiece over here, so if you keep workpiece over here, okay, so it will remove the surface undulation or polish the workpieces there. So this is the fixture here. So in this is the fixture here. In this fixture you have to keep the workpiece. Obviously this workpiece, internal surface of the workpiece you can polish by this process. Okay, so when media is coming from the bottom media cylinder to the top media cylinder, while passing through this workpiece fixture, okay, through this workpiece and workpiece friction assembly, it will polish or remove the surface undulations from the workpiece surface. So this is one of the mechanism to polish internal surface of the workpieces. So here this is a centrifugal assisted abrasive flow mechanism, CFAFF. So it is developed by Reddy et al. 2008 at IIT Roorkee. Okay, so this is the similar to the AFM process, abrasive flow machining process. What they have done, they have actually used one centrifugal rod there at the center. Okay, so at the media cylinder, through the workpiece they put one cylindrical rod or centrifugal rod. So as the centrifugal rod rotates, they are rotating the centrifugal rod from outside. As the centrifugal rod rotates, because of the centrifugal force, the internal surface of the workpieces actually removes. Okay, so here there are two forces, two actions are there. The centrifugal rod is rotating, and at the same time they are giving reciprocating motion of the polishing media. So because of this action of these two processes here, the surface finish improves, which is better than normal AFM process, abrasive flow finishing process. Now this is the magnetorheological abrasive honing, MRH abrasive honing operation by Sadiq and Sambugam. So in 2009 it is developed at IIT Chennai here. So here this is the container here. Inside the container they filled up with the MR polishing fluid. So this container is filled up with the MR polishing fluid. So that is a cylindrical fixture here. This cylindrical fixture at the external surface of the cylindrical fixture they kept their workpieces there. Now this workpiece actually rotated by an external means here. So it is rotated by an external means, and now they have applied some magnetic field here. So when they are applying this magnetic field, this MR polishing fluid here, it will become very stiff here at this zone. MR polishing fluid will become very stiff. Okay, so now this MR polishing fluid will remove the surface undulations from the workpiece surface here. Okay, so they are giving reciprocating motion also by using this spring mechanism. Okay, spring and plunger mechanism, they are giving some reciprocating motion to the polishing media. So they are giving reciprocating, as well as rotating the workpiece inside. Okay, now this magnetic field, they have used this magnetic field here. Because of this magnetic field, this MR polishing fluid will become stiff at this zone only. Okay, at the finishing zone. Okay, and as they are giving the reciprocating motion, so it will remove the surface undulations from the workpiece surface. So this right hand side picture, you can see this is the magnetic abrasive finishing process. Wang Hu, they developed this one in 2005, and Abagachi et al. Also they did some experiments over this machine and in 2005 in Japan. So you can see here they are polishing a bent tube. Okay, so this bent tube actually they are polishing. So for polishing, so these magnets actually they kept 90 degree with each other. Okay, so you can see here in magnetic abrasive finishing, these loose magnetic abrasive particles and abrasive particles are there. They will form the lines of force, magnetic lines of force. They will form chains along the direction of magnetic lines of force, and this is the equipotential line you can see. So this, now they are rotating this workpiece now. Okay, or you can rotate this total assembly also, this magnet assembly also you can rotate from outside. So what they have done, they are rotating this magnet assembly. Also they are moving this magnet assembly by using a robotic arm. So by using a robotic arm, they are moving this magnet assembly, okay, and at the same time they are rotating also this total magnet assembly, they are rotating. So because of that, this whatever the polishing media is there, it will remove the surface undulation or polish at the internal surface of the cylindrical workpiece. So this is one of the mechanism to polish internal surface of the workpiece. Now after that magnetorheological abrasive flow finishing process, which we discussed in the last class, which is consist of MRF process and AFM process, okay. So it is developed, so by taking advantage of both the process, magnetorheological finishing process and abrasive flow finishing process, so they have taken advantage of both the processes here, okay. So what are the advantages are there? So advantages are viscosity of the abrasive polishing media, so we can control from outside by using applied magnetic field. So we can control this viscosity of this media from outside by using the applied magnetic field. And also this experimental setup, as it is similar to the abrasive flow machining setup, okay. So in abrasive flow machining setup, we can polish any kind of complex geometrical surface, either it is internal or external, any kind of polishing surface you can, any kind of surface you can polish, okay. So as the machining setup, it is close to the, it is similar to the abrasive flow machining, okay. So there is no shape limitation on the workpiece surface to be finished. Now this is the key features of MRF process. So MRF process relies on the smart magnetorheological fluid, which can be thought of as a compliant lab or replacement for the conventional rigid polishing lab. The viscosity of the magnetorheological polishing medium in MRF process can be manipulated externally according to the need of the workpiece surface to be finished, and precise control of finishing forces, and hence the final surface roughness in MRF process can be achieved. You can precisely control the finishing forces by changing the pressure or by changing the magnetic field, okay. MRF process will result in a surface finish of nanometer range owing to the gentle and controlled polishing conditions. So you can get the surface finish in the nanometer range by using MRF process. But it has, this MRF process has certain limitations. So we can see that magnetic field, whatever two coils of the magnets which are applied just opposite to each other outside the cylindrical workpieces, in that case you can see there these core materials are just opposite to each other on a cylindrical workpiece, and most of the magnetic field will be there where these core materials is there, or north pole and south pole is there, just perpendicular to that, where you are not applying magnetic field vertically into that surface, there you will get the less magnetic field. Although this core material is covering the total cylindrical surface, but perpendicular to that surface, you will get less magnetic field. Or at the internal surface of the cylindrical workpiece, you will find that non-uniform magnetic field. Somewhere this magnetic field is more, and somewhere this magnetic field is less. So first limitation is the difficult to provide uniform magnetic field in the finishing zone due to the fixed coils at two diametrically opposite sides of the cylindrical workpieces which are fixed. Now non-uniform finishing of cylindrical workpiece at different points across the diameter. So that's why there is a non-uniform polishing because of the non-uniform magnetic field. So non-uniform polishing, if you are polishing a cylindrical workpiece or different cross sections also, if you are not giving magnetic field uniformly surrounding this cylindrical workpiece, you will get non-uniform polishing from the workpiece surface. So what is the solution here? The solution is that rotate the workpiece with respect to the fixed magnetic field. So you can rotate the workpiece here, or you can rotate the magnetic field itself, or rotate the magnetic field with the help of a permanent magnet or electromagnet. So you can rotate the workpiece, or you can rotate the magnetic field from outside. Okay. But in case of MRF process, as we are using the oil-based media, so there is a leakage problem. So if you try to rotate the workpiece there in MRF process, there will be this MRF fluid will leak out. Okay, it will come outside. Okay. So because we are applying huge pressure and our fluid is in the liquid state, only there where we are applying magnetic field, it will become almost solid, but in other places it is become a Newtonian fluid. It is like a Newtonian fluid. So if you try to rotate the workpiece here, it is not a feasible one. Okay. So that's why we have thought of rotating the magnetic field itself surrounding the workpiece. Okay. So by giving this concept, we have developed a new process which is called rotational magnetorheological abrasive flow finishing process. So this is called rotational magnetorheological abrasive flow finishing process. So what are the possible application areas? So it has applications in aerospace industries, automobile industries, dies and mold manufacturing industries, biomedical industries, ceramic industries, and semiconductor industries. So all these industries, it can be used for polishing very small components, any intricate components, any non-uniform components, internal surface, inaccessible areas of the components can be polished by this process. So industries, these are the industries: HAL, NAL, BRC, DRDO, BHL may be interested to use this process for polishing of their intricate components. Okay, these are the possible application areas. So now first one you can see here, this is the investment cast mill parts. Here these are the curvatures on the component. You can see these curvatures, non-uniform surface on this non-uniform surface of these components are there. So these components can be polished by the MRFA process by flowing this media through these components. So this is the aerofoil which has a very complicated surface. This aerofoil through this aerofoil you have to flow this media in such that it will remove the surface undulations from the aerofoil surface. So this is the cast aluminum component, aluminum automotive turbo component. Okay, so this is the cast aluminum automotive turbo component is there. So this component you can see at the surface, it is a non-uniform surface is there. So this is the initial surface, this is the polished surface. Okay, so this kind of surface can be polished by this RMRF process. So these kind of vane tubes which are used, compressed fitting of valves, fittings, tubes, flow meters. Okay, so these kind of vane tubes are used in medical equipments also. So these the internal surface of the vane tubes can be polished by this RMRF process. And these kind of medical components are there. So these components also can be polished by this RMRF process. Suppose gears are there. So at the mating surface of these gears, you will see there are some small bars are available. Bars are there during milling of these gears. So these bars are actually generated. Unless you remove these bars, these gears you cannot use. If you are making very small gears, these bars size is, if it is very high, in that case it will not match at all. Okay, so there will be backlash error. All these things will be there if you use this kind of defective gears. So these gear teeth can be polished by this rotational magnetorheological abrasive finishing process by flowing the media in such a way that you have to flow the media through the teeth only. Okay. So second one is the heart valves. These kind of heart valves are used in medical industries. So these heart valves, it should be highly polished. Okay. So these heart valves can be polished by rotational MRFA process. So thousands of automotive components, these components can be polished by this RMFA process. Like exhaust manifold of engine. Okay. So there are intersection of various fluids are there, various cylindrical channels are there. So at this intersection to ease the flow of the fluid, so you have to remove the material from the at the intersection surface. Okay. So rotational MRFA process can be used for polishing this kind of fluid, this kind of workpieces. So high pressure holes of diesel injector nozzles. So these also can be polished by our MRFA process. So these are the different configurations of the magnet. So we have used permanent magnet initially. So different configurations we have thought of, so that at which configuration you will get uniform polishing at the internal surface of the workpiece. So that configuration can be used for polishing all the workpieces. So these are the three configurations we have thought of. This is the first configuration you can see here. This is the south pole and this is the north pole here. So in between you can see these CFP iron particle chains are actually forming in between the south pole and north pole. Okay, but here you can see this magnetic field is not uniform inside the workpiece. So it is magnetic field, it is not uniform inside the workpiece. So we have considered a cylindrical replica. It is made of perspex. Okay, so this replica, it is made of perspex and it is filled up with MR fluid. Now we have applied some magnetic field there. Now we are observing the chains. Okay, so you can see these chains are not uniform in case of configuration 3. Now you come to this configuration 1. So in this configuration you can see this north pole, south pole, north pole, south pole, like that we have used. So now you can see here at this point, these points actually it is just 45 degree to both the north and south pole here. You can see these magnetic fields are almost uniform. Okay, 1208, 1280 Gauss, 1550, 1049, 1230 Gauss. So magnetic field is uniform in this case. Okay, so now if we rotate this total assembly here, if we rotate this total permanent magnet assembly, we will get the uniform polishing at the internal surface of the workpiece. So this is the configuration 2, second configuration, where this north pole and south pole, these combinations are kept, and here this north pole and south pole, these combinations are kept. So that's why magnetic chains are actually forming in between this north and south pole. Here also magnetic lines of force are forming in between this north and south pole. So here also you can see in second one, this magnetic field is not uniform at the internal surface. So here at the 45 degree you can see it is 10 Gauss, 1050 Gauss, 15 Gauss and 1120 Gauss. So here at this point magnetic field is very less. But in this configuration everywhere this magnetic field is almost similar and it is high also. Okay. So also we have measured the magnetic field using a Gauss meter. Gauss meter is a device which is used for measuring the magnetic field. Okay, it has a Hall probe sensor. That sensor you have to keep where you want to. This is a flat sensor is there. So perpendicular to the magnetic field you have to keep your Hall probe sensor. Okay, and it will show how much magnetic field it is crossing. It is crossing, that area is crossing. So at that point, what is the magnetic field intensity? It will measure. So from all the configurations here, after measuring magnetic field in between this north and south pole, okay. So we have found that this configuration 1 here in this case we got highest magnetic field. Okay, we got highest magnetic field in this case, then configuration 2 and 3. So this configuration 1 is actually considered for measuring for doing the RMFF experiments. So here also we have done some Maxwell simulation. ANSYS Maxwell, we have simulated this MR fluid inside this fixture. Similar to that fixture, so workpieces, here you can see these workpieces are actually stainless steel workpieces are kept at the internal surface of this fixture. Now we have applied magnetic field outside. Now we can see this, how this uniformly these magnetic fields are distributing for this configuration 1, and this is for configuration 3. So we can see at configuration 1 you will get the highest magnetic field at the internal surface. So this is the microscopic image of the MR polishing fluid, magnetorheological polishing fluid. So as I told, it consists of CRP particles and abrasive particles. So it consists of carbon iron particles and abrasive particles here. You can see these abrasive particles here, and you can see these CRP particles here. Okay. So without application of magnetic field. Now when you are applying some magnetic field, and this is your north pole and this is your south pole here, when you are applying some magnetic field here, these iron particles are forming chains along the magnetic field direction. So this is the direction of this magnetic field. These iron particles are forming chains, and in between these chains you can see these abrasive particles are held in between these chains. So here clearly visible these chains are forming. This MR fluid is prepared by homogeneously mixing 26.6% of electrolytic iron powder, purity 99.5%. So here mesh size is 250 to 300 mesh size, and 13.4 volume percent of silicon carbide abrasive with 150 mesh size, with 48% paraffin oil and 12% Fe3 bleach. So now here you can see schematic diagram. So now this north pole, south pole, again north pole and south pole, this configuration 1 we have considered. Okay. So this configuration, in this configuration all these permanent magnets are kept, and this is the workpiece here. So here workpiece, how this along the magnetic lines of force, how these iron particles are forming, and these black colors are actually abrasive particles. Okay. So these abrasive particles are held in between these CRP chains here. Now we are rotating this magnetic field. So this total assembly, permanent magnet assembly or fixture, permanent magnet fixture, it is rotated in between two bearings. When it is rotated, it will generate a relative motion. Okay, in between the workpiece, internal surface of the workpiece and the fluid, and then fluid will also rotate because we are applying this magnetic field. This inside this permanent magnet, inside this workpiece, this fluid also will rotate, and due to the relative motion between the abrasive particles and the internal surface of the workpiece, it will remove the surface undulations from the workpiece surface. So here you can see this, how these magnetic vector lines are forming in configuration 1. So these are the vector lines are there. So here from south pole to north pole, from south pole to north pole, again south pole to north pole, here south pole to north pole. So these are the vector lines. So it is, you can see here, it is uniform magnetic field is generated in case of RMFF process. So this is the excited view of the experimental setup. So same magnetorheological abrasive finishing experimental setup, MRFF experimental setup, it is retrofitted. Here it is, this zone only actually we have modified. Here what we have done, inside a fixture. So we have developed a fixture to fix the permanent magnets. So you can consider there is a cylindrical fixture is there. There is a cylindrical fixture. So in that cylindrical fixture, we kept some slots. Inside that slots, we kept our permanent magnets. Inside that slots, we kept our permanent magnets. Now this total fixture, magnet fixture, actually it is rotated. When this magnet fixture is rotated using a motor, okay. So MR fluid, because of these magnets are rotating, MR fluid inside that fixture also will rotate. Because of the relative motion between these abrasive particles and the workpiece surface, it will remove the surface undulations. And because of this magnetic field, the CRP chains will form. Okay, CRP chains will form, and the surface particles will be held in between these chains. Now, because of this rotation, there is a chance that these abrasive particles will homogeneously mix up inside that workpiece and workpiece fixture. Okay, so new fresh abrasive particles will come as an active abrasive particles. It will come towards the workpiece. Okay, it will act as a active abrasive particles. So this is the excited view of the fixture. Now this fixture, this magnet fixture, it is rotated using a belt drive, using a motor, it is rotated. So we have used positive belt drive here. This is the pulley, two pulleys are there, you can see these two pulleys. Okay, so there is a variable frequency drive. So by changing the frequency to the current frequency of the current, by changing the frequency of the current, you can rotate this motor at different RPM. Okay, so we have rotated this motor at different RPM by changing the frequency in the variable frequency drive. So this is the hydraulic unit already we have discussed in abrasive in MRFA process we have discussed. Okay, so these are the so many components are there. So this is the workpiece here. This is the workpiece, cylindrical workpiece we kept here inside. Okay, and outside we have kept this magnets, magnet fixture. So now this experimental setup looks like this. This RMRFA experimental setup, it looks like this. So now what is the advantages of rotation? So how many forces are there? So what we have discussed in MRFA process, because of this reciprocating motion, one radial force will be generated and one axial force will be generated because of this reciprocating motion. And magnetic force also will be generated. So this magnetic force, direction of magnetic force and radial force both are in the same direction. So this magnetic force is perpendicular to the workpiece surface. Okay, so what is the how much magnetic field magnetic force will be generated? It is V chi H into gradient H. H is the applied magnetic field, chi is the magnetic susceptibility, and V is the volume of the fluid. Then radial force, it is proportional to pressure. How much? So radial force in case of this MRFA process, it is proportional to pressure, K into P. K is the proportionality constant. Centrifugal force also, because of this rotation of this fluid, centrifugal force will also generated. So this centrifugal force can be given as m r omega square. Omega equal to pi dn. Okay, this is the diameter, n is the RPM of the magnets. We can assume that these magnets will rotate, this fluid will rotate at the same RPM with the magnet. So there is no lag in between this. There is no lag in between this RPM of the magnet and RPM of the fluid. Okay, so what are the indentation forces there? So the centrifugal force will act perpendicular to the workpiece surface. So indentation force, total indentation force is radial force plus magnetic force plus centrifugal force. This total force will give the indentation to the workpiece surface by the abrasive particles. And in case of MRFA process, there is no centrifugal force, only this radial force and magnetic force will act as a indentation force. Also, due to this rotation of this magnet, one coriolysis force will also generate. This coriolysis force can be given as 2m m cross b, omega cross b, 2m omega cross b. M is the mass of this abrasive particle, omega is the rotation of the magnet, okay, and b is the velocity. So indentation due to the combined effect of magnetic force and centrifugal force. Cutting force is also resultant of the tangential force and axial force. So cutting force is due to the axial force, also due to the tangential force. So this resultant of this tangential force and axial force will give the cutting force. So path followed by the active abrasive grains on the workpiece surface is helical. So this path followed by the active abrasive grains on the workpiece surface is helical, provides a higher finishing rate than the MRFA process. So now in MRFA process, these abrasive particles will traverse along a linear path. But in case of this RMFA process, these abrasive particles will rotate in a circular path. Also at the same time, you are giving this reciprocating motion. So that's why all the abrasive particles will follow the helical path. So because of this helical path, whatever the area covered by the single abrasive particles is more in case of RMFA process than MRFA process for the same cycle time. Okay. So RMFA process, in RMFA process, abrasive particles will take more path, will follow the more path into the workpiece surface. So path followed by the active abrasive grains on the workpiece surface is helical, provides high finishing rate than the MRFA process because it is taking more path. Uniformly finishes the workpieces like honing operation. So it will, like in honing operation, you can see this workpiece is kept fixed, and this honing tool actually it is reciprocated, also at the same time it is rotated. So it will generate because of this reciprocating motion and the rotational motion, it will generate cross-hatch pattern. So these cross-hatch patterns, whatever the scratch marks or lay marks by the abrasive particles, it will generate the cross-hatch pattern. Because of this cross-hatch pattern, it helps in oil retention in case of RMFA process. So here you can see in RMFA process, so this kind of helical motion is given by the abrasive particles. So abrasive particles will move in this helical path. So these are the force diagram here. So indentation force in case of MRFA process is magnetic force plus radial force, and then that is the axial force or cutting force is there. After indentation, this abrasive particle will cut the surface undulations from the workpiece. But in case of RMFA process, there are three forces are there: radial force, magnetic force, and centrifugal force. So here centrifugal force is added here in case of RMFA process. Also there is one more force which is called coriolysis force, that is also added in case of RMFA process. Okay, so total force in case of rotational MRFA process, the total force is axial force, this resultant of this axial force, and This is the axial force, and also this tangential force will give the total cutting force. So here indentation is due to the combined effect of magnetic and centrifugal force. Cutting force is the resultant of tangential and axial force, and path followed by the active abrasive particles on the workpiece surface is helical and provides higher finishing rate than the MRFA process, and uniformly polishes the workpiece like in honing operation and generate a process pattern which helps in oil retention. So you can see here these abrasive particles are here at the internal surface of this workpiece. This kind of helical path it generates. So what is the equation of this curve is RW, so radius of this workpiece, cos Ti, RW, sin Ti j, sin T j, and CT k. So this is the equation of this helix. And what is the helix angle? Helix angle is tan inverse 2 pi c by 2 pi RW, or tan inverse c by RW. And arc length of the helical path, total arc length of the helical path is S equal to SW by c root over RW square plus c square. And V, here in this helix angle, this c is the axial velocity by rotational velocity, VA by VW. So VW is 2 pi n by 60. So you can see here with the rotational, with the increase in the RPM of this magnet from 50 RPM, 100, 150, 200, and 250 RPM. So helix angle actually it reduces. So helix angle reduces. So if we increase more RPM here, increase RPM here, so in that case at certain time, okay, so helix angle will be parallel to the okay. So calculate a helical arc length. So if we increase the RPM of this magnet, you can see this arc length also increases. Arc length increases means it traverses more path than normal MRFA process. So advantages are of RMFA process: uniform polishing throughout the workpiece surface due to the rotational motion of the polishing medium surrounding the workpiece surface, better control of the finishing forces, because we have added one more process here which is called centrifugal rotational motion. Okay, so better control of the finishing forces through the control of the rotational speed of the polishing medium along with the existing reciprocative motion. So this additional force other than the axial force acting on the abrasive particles due to its rotational motion of the magnet enhances the capabilities of the abrasive particles to abrade surface undulations from the hard workpiece surface like stainless steel. So due to the longer traverse length, so because it is traversing more arc length here in case of RMFA process by the abrasive particles touching the workpiece surface, because of helical path motion of the polishing medium in RMFA process, there is a more interaction of the abrasive particles because it is taking the more path, more interaction of the abrasive particles with the workpiece surface, hence better polishing than MRFA process. So higher polishing rate will nanometer per cycle than MRFA process. It has higher polishing rate due to the extra forces like centrifugal force and tangential force, due to the rotational motion of the polishing medium and helical path motion of the polishing medium. In RMFA process, the abrasive cutting works generate cross hatch pattern on the finished surface of the workpiece like in honing operation, which would improve the lubricant holding capabilities of the finished surface.